The round.
Yeah.
Well, that doesn't matter.
Okay, so here's the story we're going to investigate then, right? This guy's he's gonna lean out and he's gonna shoot a bullet straight up in the air from coated in slipstream, right? He's gonna shoot it straight up in the air with a muzzle velocity of 1,000 meters per second. So that's pretty high speed, but it's reasonable. And we want to know, we're going to answer a bunch of stuff. Let's answer the questions: how high does it go? How long does it take to hit the ground? How about? And how fast is it going when it hits the ground?
So it's going to go to the ground.
Right. So it's going to go down. It's going to go straight up, and then it's going to come right back down by the building. There's zero wind. It's ideal conditions. Okay.
No, wait. Does it have the one stuff on it?
Yes.
Okay.
Yeah, it does. Yeah, it's got slip rim on it, so it's going to go. So it's going to go up and turn around and come back down.
So it's starting on top.
Is like the
Yep.
whole thing coated, like including the casing?
Oh,
It might not ignite.
Ah, there you go. Okay, that's true. All right, so let's write down the stuff that we know. Right, so here's our picture. Let's write down the kinematic quantities. When are we starting the video camera?
0 seconds.
Which is when?
When he shoots it?
When he shoots it, right? Okay. So then what are tell me some initial conditions. What do we know?
It's going at 1,000 meters.
Okay, so V naught equals positive 1,000 meters per second, right? Why is it positive? It's going up. Okay. Equals positive 1,000 meters per second. What else do we know?
It's going at 9.
Okay, so we know. Okay, so the initial position, let's say, the initial position is positive 829.8 meters. Okay? What else?
It's going at 9.
Okay. All right, good. So we know the acceleration is equal to g, right? Which is negative 9.8 meters per second squared. Okay, good. So we know a couple things. Now we know we're asking a couple different questions, but which one are you thinking of, Laura? Final position is going to be what? Okay, so when it lands, it's going to be 0, isn't it? Right? So when it hits the ground, the final position will be 0, right, for that question. Let's hold off on that one, and let's do the questions related to the how high it goes one first. Okay? So what do we know about the how high it goes situation? There's something we know about that too.
I'm just asking hypothetically, could we have said starting point was at 0?
Sure.
And the ending point was at negative 8?
Absolutely. It makes no difference, because is there one place in the universe that we would automatically define as being? No. It's all relative. It doesn't make any difference. As long as you define your reference frame, you can use any reference frame you want. Good question. Yeah.
Finding the height is going to be when velocity is 0.
Okay, good. So if we're trying to answer the question, let's kind of color code this. If we're answering the question, how high, then that's supposing that we're going up to the apex. The apex is going to be that one frame in the video where the velocity is 0. Imagine we've got a really expensive video camera that it's vector sensitive. So it tells us all this stuff. We're going to find the frame at the top where it shows the velocity vector as having a magnitude of 0, right? Okay, so V final equals 0. What are we trying to find for this question? What are we trying to find? The time, aren't we? Right? We agree? Trying to find the time. So we're asking the question, what's t equal? Okay? So now, if you want to get out your little sheets, which equation matches that information? Actually, we're finding out how high, not the time. What am I saying?
No.
We could also answer the question, if we wanted to, how long does it take to get there, if we want to. But we're really trying to answer here, the question I asked first was, what's the final position, right? Agree? Okay.
Yeah, 4.
Okay, so we've got equation 4 we could use, good, because there's no time, right? Okay, so that's the equation final speed squared minus initial speed squared equals 2a delta x, right? And delta x is just v final minus v initial, right? Everybody agree? We could do this, though. It's convenient for us in this equation to solve for delta x. So let's just hypothetically say that delta x was 1,000 meters. It's not going to be. If delta x was 1,000 meters, what would have been the maximum height the bullet got to? How'd you get that? Added it to the starting position, right? Because displacement is the change in position, right? Okay? All right, so then let's solve for delta x here. So if I isolate delta x, is anything 0 that we can just cancel out? Yes, ma'am. Okay, but we asked a couple questions. Remember, we said we're going to shoot this gun up in the air. We want to predict how high does it go, how long does it take to hit the ground, and how fast is it going when it hits the ground. Okay, so the first question we'll answer is just how high it goes. Then we'll move on. You were correct on the second one. You knew what we're really saying there is we know what the final position is and we'll solve for t. So we'll get to that one. For this question, though, we're going to see how high it goes before it hits the apex. Anything when I'm solving for delta x here, I'm going to isolate that, right? To make things easy, are there any 0 values I can cross out right away? Final velocity, right? Final velocity is 0. So I can just eliminate that one. So that makes the algebra easier, right? All I've got to do is divide both sides by 2a. Everybody agree? So then we end up with displacement equals negative initial speed squared divided by 2a, right? Okay, so now we can just plug and chug. So I get negative, and I'm not, keep in mind here, that negative is not part of what's being squared, is it? Right? It's initial speed squared times negative 1. So I get negative 1,000 meters per second squared, right? Divided by 2 times negative 9.8. If I want to, let's not include units. We know we're doing it right. We'll be careful. Standard units, right? So we can put that in our trusty calculator. And notice that the signs are working out, aren't they? Right? We're going to get a negative divided by a negative, which means that, we'd expect to have some positive answer, right? It's going to go pretty high. Okay, so all right, so what do we get? Negative the quantity. Actually, I don't even, on my calculator, I want you to notice something. I'll make a point here. Negative 1,000 squared. If I hit enter, am I going to get a negative or a positive value back? Negative. Give me negative. Yeah, our calculator knows that if you want to, that negative by order of operations comes after the squaring part, right? So just remember this in your math classes, if you, or in here too probably. If you ever want to square a negative number, what do you have to do on the calculator? Got to put in parentheses, don't you? Yeah. So negative 1,000 squared divided by the quantity, because I'm multiplying stuff, 2 times negative 9.8 gives us, that's big, positive 51,020. How many sig figs do I get to keep here? 4. 2. How come? Okay, because the least precise measurement is the acceleration in this case, right? I could have given you more sig figs on that, but I didn't, so it's only got 2. I'm sorry? Oh, okay, so yeah, what about velocity is ambiguous, isn't it? Let's say let's say we measured that, it's exactly, to 4 sig figs, it's 1,000. That's a good it's a good point, though. That's ambiguous because we didn't write it in scientific notation. Okay. On the problem sets, always assume that if you get a number like that, that it's measured all the way out to the last digit. Okay. And honestly, we don't need to get too hung up on that stuff. I mean, throughout the year, you are going to have to pay attention to sig figs on these problems, but that's not really the part that I'm interested in. Okay, so this is how high it goes. So 51,000 meters. That's a lot, right? How high is that? 51,000 meters. Let's take this number while we're at it. Let's just kind of get a sense of how high that is. So that's 51 kilometers, right? Here's how I always remember it. A 10K race is 6.2 meters. So 51 kilometers, that's like a big deal. I mean, then you're looking at what, 31 miles high? Does the bullet really go that high? Not even close. How come? Because air resistance is massive. Air resistance is, the thing about air resistance, and we'll talk more about this later, air resistance is tricky because friction is a higher order effect. You have to model it with calculus with a differential equation. It's not a linear fit. The faster you go, friction increases non-linearly. And so, if you try this sometime. If you're going, say you're going 35 miles an hour down the road, put your arm out the window. And then put your arm out the window when you're going 70. And you're going to notice, you'll be able to tell. You get more than twice as much resistance to your hand, 170, as you did when you're going 35. So it's not a linear thing. So when you're going that fast, 1,000 meters a second, friction is like a brick wall. I mean, it pushes on that bullet really hard initially. So it won't go nearly that high. But if we were to launch this up in space, if we were, say we evacuated all the atmosphere off the Earth, and we did the same experiment, somehow we had to ignite we introduced just a little bit of oxygen in the chamber to ignite the bullet, how about? Then it would go this high, right? It'd go pretty high. So once again, we've got this fancy slippery and stuff on the bullet, so we're assuming it does go that high. Let's see how long it takes to get back down to the ground, okay? Yeah. All right, so part A, we said it took, and then we forgot to subtract away the 829, didn't we? Right? So technically we should do this, right? We should take this answer and we're going to, add to it, sorry. We're going to add to it 829.8. And then we can round it. Well, it doesn't change it much, does it? So we go up 52,000 if we round it, okay? And I'm going to put the approximately equal to, because we rounded it. Wow. All right. Okay. All right. Let's see how long it takes to get back down to the ground. Okay. So now, Lauren, what do you say about that? If we're going to go to part 2, where we're saying now we want to know how long until it hits the ground. What was the initial condition we had to use, or the final condition we had to use for that one? What did we say? The final position is 0, right? Because now we're asking the question, that was what we looked at for part 1. Now for part 2, we're looking at how long it takes to hit the ground below, okay? So here we'd know that x equals 0, right? And which equation are we going to use there then? If we know all this stuff is, except the velocity is now, final velocity in this case, would not be 0 anymore, would it? Right? So down here, let's rewrite all of our conditions. So we know initial velocity is 1,000 standard units. We know acceleration is negative 9.8. and we know initial position is 829.8. Right? We're trying to solve for t, aren't we? So which one's going to work there? 3. Yeah, that's equation 3, isn't it? So that's the one where we're going to say, it's better. We're going to say final position equals initial position plus initial velocity times time plus 1/2 acceleration times time squared, right? That make sense? Okay, so we're trying to solve for t, so let's plug in values. So we get 0 equals 829.8 plus 1000 t plus 1/2 times negative 9.8, right? So does everybody agree 1/2 times 9.8 is just 4.9? So I'll make that minus 4.9 t squared. Does everybody see that this stuff right here just becomes negative 4.9? Okay. So what kind of an equation is that? Quadratic, isn't it? Right? So we got a quadratic equation. We want to solve this thing. Are we going to try to factor that? No. We could use the quadratic formula, but let's just cheat a little bit and use technology. How about, right? So this is a good little topic for discussion. How can we do this most easily with technology? Okay, we could, yeah, we've got some options, don't we? Let me grab this in piece and we'll go to a new page and we'll talk about technology. How do we, you guys can throw out some suggestions here. Okay, so that's what we're trying to solve, right? Let's go to graphing calculator first, how about? So what could I do with a graphing calculator? Okay, I could use Aqueduct. That's fine. I don't have Aqueduct, but I've got something better that you should know about. I know you kind of are attached to Aqueduct, but try this. If you go to apps, bust out your graphing calculators, Polysmult 2 is better. That's polynomial simultaneous equation solver. Okay? Oops, I gotta go down this way, don't I? So 8. If you don't have that, let's load it up on your calculators. It should be on there though, I think. If you just bought a, if you've got a reasonably new one, it's on there. And if you don't, I can put it on there for you if you have an older one. So we go to this. Have you seen this? No? Okay. So we want polynomial root finder, which is 1. Okay. What's the order of our polynomial? 2. It's quadratic, right? So we go to 2, and that's the default. What do we want, real or imaginary solutions? Let's just stick to the real ones, right? We're going to get 2, and they're going to be real. Do we want auto or decimal? Let's go, I think auto will just give me decimal in this case. And everything looks good. So then we'll just go down and hit F5 for next. And now we're just going to enter the coefficients. How about that? So my coefficients are what? What's the coefficient of x squared? For me, it's t. Careful. No. Negative 4.9. Okay. And then I think I go, nope, I think I have to hit enter. There we go. Again. Oh, that's where you change. You could change the sign there if you wanted to a minus. What's b? 1,000. Okay. See? 9.8. Okay, good. So now we hit enter, and we'll just go down to F5 and hit solve. Okay, look what it does. Okay. What's really cool about this, though, what this does that Aqueduct doesn't do very well is it'll give me complex solutions with imaginary parts too, either in polar form or in A plus BI form, right? So it does some other stuff that's better. So we got two answers. Let's explore these. We get to keep, how many sig figs did we say? 2? Okay, so to 2 sig figs, what are our times?
Negative 0.8.
Okay, so t equals negative 0.83 seconds, or t equals 200 seconds. So that is, what is that? That gives us a little more than 3 minutes, doesn't it? 3 minutes, 20 seconds. Okay. Well, which one are we looking for? 200 probably, right? Math gods, they gave us some nonsense up here, right? Or did they? How do we interpret that? This is the right answer. That's the one we're looking for, isn't it? Right? But what's the other one mean? How much before the time? Yeah, this is, I mean, not that this is, really, what we wanted was the 200, and if we were doing this, if we were engineers, we were whatever, we would just move on. But the physics gods have told us something important. Let's see if we can interpret the wisdom that they bestowed on us here. What does that mean? What does that mean? It's describe the situation, and you're right, it has to do with the negative 0.83 seconds means we're going to go back almost a second before we started the video camera.
It's assuming that it never started at that moment, but it started beforehand.
Okay.
And that's...
You're right. You're on the right track. You want to add something to it? Yeah.
Saying that, assuming that it's going the same speed as when it left the muzzle, that if the acceleration or velocity, whatever was going in that negative direction, it would take like a second.
Okay.
Wow.
Okay, the acceleration is always negative and constant. But think about this now. You want to throw something in? So, right, it's saying, think about the conditions that we imposed on this problem. That when we petitioned the physics gods for an answer here, we said, we want to know, they're very literal, those physics gods. You got to be careful with them. We said, we want to know what are the times at which these conditions exist. The position is 0. The initial velocity at some time earlier, right, is 1,000 meters per second. The acceleration is constant and negative 9.8. And at some time earlier, the height was at 829.8, or at some, right? Does that make sense? Maybe earlier or later. I shouldn't say earlier or later. We know that at some point, there's going to be a frame in the movie where the velocity is 1,000, positive 1,000, and the height is 829.8, right? We want to know, and the acceleration is constant, negative 9.8. We want to know, consistent with those conditions right there, if this represents a frame in the movie, right, then when is this true? When is the position equal to 0, right? Well, one time is, what did we say it was? 300 seconds, is that what it was? 200 seconds later, right? 200 seconds later, 200 seconds after that frame, the bullet's going to hit the ground, okay? But couldn't we just as easily have fired the bullet from the ground, right, at some initial velocity a little higher than 1,000, right? But now imagine that instead of having a rifle, we just held out a pipe instead of the rifle. And the bullet goes zooming up through the pipe, and as it goes through the pipe from the ground, it's traveling at 1,000 meters per second. And the pipe is held at a height of 829.8 meters above the ground. See what I'm saying? You get that? How long would it have taken to get from the ground level up to the pipe? What it was, 8-something seconds? 82 seconds or something? Question, Laura? Yeah. Clearly, that's not the question we were interested in, but they gave us that answer, and that's what it would mean, right? That make sense? Okay. How fast is it going when it hits the ground, how about? Last question. How are we going to answer that one? Well, now we've added an answer for t, haven't we? So that might be helpful. What do you think, Richard?
You could start with its highest point of its velocity is 0.
We could. We could do that, or we could do, well, we have a bunch of choices. We could even use this information, just ask a different question. What would we be looking for here? We'd be looking for the final, right? Okay, so is there an equation that would work there? If we know the acceleration and we know initial velocity, we actually know time because we calculated time, right? Does that make sense? And we could use that calculated value if we want to. So one possibility, if we use time, would be which equation? 2, right. Good. So we'd have V equals V naught plus a t, right? Okay, what if we didn't use time? Is there a way we could do this? 4, right? Do you see that? We could do V squared minus V naught squared equals 2a delta x, right? Does that make sense? Okay. Either way, we should get the right answer. Now, which one of those seems maybe better to you? One of them definitely seems better to me.
The first one?
The second one, how come? I think I heard it. How come? More measurements meaning the time is kind of polluted, isn't it? Right? Because we've calculated the time based on some other measurements, right? And so, I mean, you could accumulate some rounding error. If you use time, here's the way, and honestly, you'd think that this is something that would be resolved. But I think this is taught incorrectly a lot of times. What you should do with this is if you use time, you should use the unrounded version of time and only round, the rule is you should only round the last measurement, right? So if you do use an intermediate calculated quantity like that, you want to use the unrounded version of time and then round the answer that you get for final velocity. Does that make sense? Okay. Let's go ahead and just use this one though. Based on the conditions that we've imposed there, what do we got? We know we're trying to solve for v, right? So if I solve for v, how do I get v by itself? Got to add that to the other side, right? So I get v naught squared plus 2a delta x, and then I'm going to have to square root that whole thing, right? Everybody agree? Okay. What if we plug in those values then? What do we get? Let's just plug them into the calculator. How about you guys can read them off to me. Just plug them into the calculator. You remember what they are. So let's see. We get the square root. Let's clear all this stuff out of here. I think you have to quit this too, just so you know. I have to go up to F1 and quit the app. Okay? So then we're going to get the square root of V naught is 1,000, right? So 1,000 squared plus 2 times negative 9.8 times, what's my displacement?
Can we borrow 2 grubber?
Absolutely. Help yourself. Say it again. Negative 829.8. How come it's negative? Okay, good. Because I'm starting at the top of the building and I'm ending at the bottom of the building, right? Okay. So we get times negative 829.8. Is that what it was? Okay. and that gives us the answer 1,008. So about, if we round to 2 sig figs, I just get about 1,000. It's slightly more though, isn't it? Right? What if we were to have been more accurate? It makes sense that it would be a little bit higher than 1,000, doesn't it? Which within rounding error though, it's not. Had to be a little bit more though, didn't it? We sense it had to, because it had to get up to the building. Or when it came, let me ask you this, another way to say this. How fast is that bullet going? If I shoot it up in the air and then I hold my hand out to grab it, how fast, we don't want to do that probably. How fast is it going?
1,000 meters.
1,000, right? Because we'll talk more about that too, and that has to do with the symmetry of that problem, right? Interesting use of symmetry, so just file this one away. We're used to talking about symmetry as being a geometric thing, right, in math. In physics, a lot of times we talk about symmetry with respect to time, right? And so that's a different way to look at it, but it works just as well, and it's probably more useful in many ways. So it comes back down bias going 1,000, but it's still accelerating, and so it's going to accelerate a slight bit more before it gets to the ground. It's not going to pick up much speed, though, is it? Because it's going pretty fast, so the travel time to the ground is pretty small. Does this seem reasonable, though? Because this is a big part of being a physicist. Let's just say that we had measured this stuff more accurately. This was to 4 sig figs. This was to 4 sig figs. To 4 sig figs, this is like negative 9.80 something. So it's almost exactly 9.8. So what if we had gone out to 4 sig figs and been able to keep all this stuff? Does that seem reasonable that it would be 1,008 based on our last findings? Does that seem, tell me why, defend that answer. Say, yeah, that sounds about right because what? What if I go, whoops, where are my time answers? Right there. How could you leverage those, what we already knew, to say, yeah, that seems about right? 1,008 meters per second is the speed when it hits the ground. What do you think? Do you see what I'm asking? I want to know, you could look at this and say, at one level you could say, that's a little bit higher than 1,000, so that's good. But you could actually look at this and say 1,008. That makes sense that it's 1,008.
With that first one, the negative 0.83,
Okay.
Would that be the time that it takes from like it goes all the way up and then comes back down to where you shot it from? It would only have 0.83 seconds
Exactly.
until it hits the ground to accelerate.
Because it's exactly symmetrical, right? The trip up is equal to the trip down. So the physics gods already told us that it would have taken 0.83 seconds for that bullet to get from the ground up to the top of the building. So if we run the movie forward, it's going to take that long for it to get from the top of the building back down to the ground, too. If we just drop an object, and it doesn't matter if we drop it, well, let's take a couple of questions. If I drop a stone from the top of a high cliff, how fast is it going after 1 second? 9.8 meters per second down. How much speed did it pick up? 9.8 meters per second downward, right? What if I throw the rock up at 19.6 meters per second from the top of the cliff? After 1 second, how fast is it going? 9.8. How much velocity, how much has the velocity changed? 9.8 down, right? Make sense? What if I throw it downwards at 10 meters per second? How fast is it going after a second? 19.8. What's consistent there, right? It's always going to gain 9.8 meters per second of velocity downward, right? So if we shot the bullet off an infinitely high cliff, just bear with me. Whatever its muzzle velocity was, say 1,000 meters per second, after 1 second, what would the muzzle velocity be? 1,009.8, right? Well, what's our muzzle velocity? 1,008. That's a little less than 1,009.8 because it traveled for a little less than a second. So that, we don't have to do the exact calculations, but that, you see how that makes sense? We look at that and say, that's very reasonable. Yeah? All right, that's a lot. That's a lot. I'll put the gravity or the free fall assignment up. How much time we got?
8 minutes.
8 minutes. You can work a little bit. That's fine. Work a little bit. I'll throw the assignment up. Maybe if you have a question or two, you can get those answered.